We got through everything for the assignment that's due on Wednesday. How many people are done with that, by the way? Totally done. 1.3 practice 1. Again, how many people are done with all that? Okay, good. All right, so you'll have a chance. Here's the plan then. I'm gonna fill in the rest most of the rest of section 1.3. 1.3 is a pretty big section, reviewing, solving equations. That's not going to take us forever today. You probably get a little work time maybe at the end. And then tomorrow is a day you guys are going to benefit from being ahead. You're going to get a day tomorrow to wrap up the 1.3 practice 1 assignment, which means I would expect questions from that. Okay, just do the following morning. And then if you're finished with that, you can work on this other assignment that I'm going to give you. I'll make it online today at the end of the school day, but this will be due Thursday. Okay, and this other stuff we're talking about. So what's this about? So this is kind of some other little minor topics that surround this idea of solving equations using PEMDAS. Okay, this is a good news slide right here. This one reminds us about a really simple shortcut for dealing with certain kinds of equations. So if we go back to geometry class last year, you would have done some of this. What's a proportion? Okay, a proportion in math, it just simply means if I have a fractional equation. So if I have a single fraction equal to a single fraction, we love those in math because those are really easy to solve. Okay, what's the trick for solving a proportion? What did you do to solve a proportion? Remember? You can, but cross multiply. Yeah, rather than we don't even really have to think about clearing fractions or any of that stuff. If I have one fraction on the left side and one fraction on the right side, I can always just cross multiply. So here's an example. If we look at just this template up here, let's say we've got the fraction a divided by b equals the fraction c over d, right? So if we want to get rid of the fraction and turn this into a simple equation, a non-fraction equation, where all the fractions are gone, all we have to do is just cross multiply. So we've got this cross product is equal to this cross product. So I've got b times c is my red cross product is equal to a times d. That's my blue cross product. And then from there on out, there's no fractions, so it's much, much easier to deal with. Let's look at a couple quick examples. So what about this guy right here? So what do we got to do here? We have a proportion, correct? I have a single fraction, 5 over 3 equals the single fraction 2 divided by x plus 4. It doesn't matter that there's an x plus 4 in the bottom. It's still just a single fraction, right? Okay, so what do I do? Okay, so we're gonna cross multiply, right? So we got two cross products here. I've got this cross product. What's 3 times 2? 6. That's going to be equal to the other cross product. Gage, what was that again? Okay, how'd you get to 5x plus 20? What'd you do? You distributed. Okay, so what you really did is you said 5 times x plus 4, but because x plus 4, there's 2 terms in that, we have to write it as a quantity and put it in parentheses, right? And then from there on out, now this is easy. I just distribute the 5 and isolate the x, right? So from there on out, it's really simple stuff. 6 equals 5x plus 20, and now you can isolate the x easily. Okay, the trick I wanted to point out, though, is that cross multiplying. It gives you an easy equation to deal with. One more. How about this one? Let's set this one up using cross multiplication. Okay, so we've got 10 times the quantity of 2x minus 8 equals, now let me get somebody else pitching in here. Your goal should be to try to make one contribution every day, and you can feel great about yourself. Okay, good. So then the other cross product is going to be 8 times the quantity, 5x minus 9. And now that's looking a lot better, isn't it? Right? If I just distribute the 10 and distribute the 8, this is not going to be a difficult equation to solve. So what do I get then? Minus 80, good, equals. And now we can deal with that, right? Okay, give me thumbs. How are we doing on that? Okay? All right, so there's one trick. Proportions are easy to deal with. Okay, I want to look at this one also. There's the reason I want to do this is I want to focus on the vocabulary. When you get up to Algebra 2 level, this is a college prep class, right? When you get to Algebra 2 level, the questions start to become a little bit more difficult. They start to involve more parts, and there's more specific vocabulary we got to be familiar with, okay? So let's see if we can deal with this question. And I'll tell you what, this is not really a very difficult question, but you can't get wigged out by all the language, the evaluate and satisfying and all that stuff. You just got to kind of calm down and just read through it and see if you can think about what that vocabulary means. Evaluate z squared plus 3z for the value of z, blah, blah, blah. We don't even worry about the second part for now. Let's see if we can just wrap our brain around what's the first part of this question asking us. What is this saying right here? Evaluate z squared plus 3z for a bunch of other stuff. Somebody knew. What's that mean? What's evaluate mean? See if you can remember that from before break. Yeah, Leo, what do you got? Okay, which is true. We're going to get to that stuff, but there's a specific thing that evaluate means. Now, I'll take you back to what we talked about prior to roundup. Value is our math word for number, right? Does that help? So evaluate. Say it again. Say it again. Well, not really estimate. Evaluate. Whenever you see evaluate in math, you're happy because these are easy questions. Yep. Okay, I mean, look at the numbers that are present. Okay. They don't really give us the number we're interested in yet. But when I say it, think back to problems like in example, how about problem set 1.2, 1.2 practice. I can't remember if we had 2 practices in that section or not. Yes, ma'am. There it is. You're plugging in a value. That's what evaluate always means, is plugging in a value, right? So when we evaluate this expression, z squared plus 3z, what that means is we're going to plug in a value for z in this expression, z squared plus 3z, right? How did we do that? Think back to what we did, back in section 1.2. Remember that our process, when we're going to evaluate an expression, we always are going to trade the variables that we're going to plug numbers in for. In this case, z, right? We're going to plug in a number for z. Remember what our strategy was. We're always going to open up an empty quantity where we used to have the z so we can pour the value into that quantity, right? So we get some quantity squared, some number squared plus 3 times some number. And the numbers I'm going to pour into those quantities are whatever the value of z is. Okay, now the difference this time compared to back in section 1.2 is that they didn't just give us the value of z. We got to do a little work for it. So what about the second part? What's all this stuff asking me to do? We want to use the value of z satisfying that proportion. How am I going to figure out what value of z to dump into my expression, z squared plus 3z? What's that mean? The value of z satisfying this equation. Say it again. There you go, solving it, right? We're going to solve the equation and we're going to find the value of z that works, that makes it true, the solution, and we're going to take that value of z and plug it back into my earlier expression. Okay, give me thumbs on the concept here. Okay, good. So now let's put it into practice. How are we going to solve a proportion? Cross multiply. Good. So we've got this cross product, right? 2 times the quantity 2z minus 7 equals this cross product. 3 times the quantity z minus 4. Okay. All right. So now let's use this as an opportunity to just review stuff from before roundup. Okay, I know many of you have finished the assignment up. You've had plenty of practice on it. But let's just go back and let's look at this PEMDAS approach again for just a second. So can I use inverse operations yet? Can I isolate z yet? You're right. How come? Ah, good. There's two z's, right? So what? And I can't use inverse operations and isolate until I can point to a single z. So I got to simplify. Well, what does that amount to? What do I have to do to simplify here? Distribute. Okay. So we can distribute the 2, we can distribute the 3, and that's going to give us what? 4z minus 14 equals 3z minus 12. Now what? Still got 2 z's. What should I do next? Okay, good. I'm going to push the z's to the left side, aren't I? So I can have a positive number of z's. So we'll subtract 3z. Good, and that gives us 4z minus 3z is just z, right? Z minus 14 equals negative 12. Last step. Add 14. Good. Okay, and we end up with the result. Z equals negative 12 plus 14 is 2. Right? So now we can go back to part A and we know the value to plug in. So we can evaluate the expression. So we're plugging in where we used to have z's, we're plugging in 2's, and now we can just simplify, right? What's 2 squared? 4 plus 3 times 2. So 10's the answer to that question. Okay. Give me thumbs. Good. There's a lot going on there. Lots of moving parts. That's good. Okay, so special cases. All right, so I want to look at what happens when you solve an equation and weird stuff happens. There's really 2 possible things that can happen. Let's look at both of these. So what about this first one? I'm trying to solve for c, but I've got lots of c's up there, right? So I've got to simplify first. You could all tell me, I'm sure I'm going to distribute that 3, right? So if I distribute distribute the 5, not the 3. If I distribute the 5, I'm going to get 1 plus 3c equals what? Okay, plus 8c. What else could I do on the right side there? Okay, good. Combine like terms. So what is negative 5c plus 8c? Positive 3c. So then I end up with 1 plus 3c equals 5 plus 3c. Okay, combine like terms. Yeah, look what happens. I can push the c's to either side and I get the same result here, don't I? If I subtract 3c from both sides, the variables all cancel, right? So what happens, here's a case where when we're doing the algebra and we're trying to isolate the variable, in the process of doing that, the variables just disappear. And what I'm left with then, in this case, is the statement 1 equals 5. True or false? False. How do we interpret that, do you think? If I solve an equation, the variables disappear and I get a false statement. What's that trying to do? What are the math gods trying to tell me? Say it again. Undefined. Okay, undefined. So you're implying the right thing. I know you know the right thing, but how would we describe it? See if we can find a different way of describing it rather than undefined. That is a math word that we talk about a lot in calculus. What is it? How do we interpret that? How often is 1 equal to 5? Never. So how many solutions are there? 0. There are none, right? There are no solutions that are ever going to make this work. The variables went away and we got a false statement. So what that's telling us is there are no solutions. Okay, makes sense? You've probably done stuff like that before. I'm going to introduce one more word that goes with this that's going to be necessary on the homework. The 1.3 practice 2 homework that I'm assigning today. When you see something like that happen, this is what we call an inconsistent equation. Okay, if there's an equation that when we solve it, we end up with no solutions, that means that's what we call an inconsistent equation. Okay, do I think it's really important for you to know that word right now? Not so much. I'll be totally honest with you. The reason I am teaching this to you is because when I built the assignment, The only problems I could find in all of the online textbooks were ones where you had to know that word. So now you know it. You know that these two things go together. If you've got no solutions, this is what we refer to as an inconsistent equation. It's really a good word to learn, though, because we're going to talk about this later in a little different context when we talk about systems of linear equations. So it's good that you get a sneak peek at that word for now anyway. It's good. It's a good thing. So how about this other one? Same kind of thing. If I've got two x's, so I have to simplify a little bit. Simplifying means I'm just going to distribute the -8, and I get on the left side 40 minus 8x. On the right side, I get -8x plus 40. Same kind of thing, right? I'm going to push the x's either to the left or the right, and it doesn't matter. They disappear. When I add 8x to both sides, look what happens. The variables cancel just like before, but this time something's a little different. That's true, isn't it? 40 equals 40 is a true statement. So now how do we interpret that? I think I heard some people saying it. I say it again. Did I hear it? Infinite solutions? There you go. Infinite solutions. Did I hear that somewhere out there? Thought it. Maybe I'm just like inventing these things. Did you say it, Gage? Okay. So infinite solutions, probably even more precisely, you probably said something like this: all real numbers, right? Do you remember doing that last year, year before? So here's the deal. If you solve an equation, the variables disappear, and I get a true statement, then that means that it doesn't matter what the variable is. There's no variable in my answer. It's completely irrelevant what the value of the variable is. I'm always going to get a true statement anyway. So that means that the solution is all real numbers are solutions. You can put any number in it, it's always going to work. Our math word for an equation like this is what we call an identity. Identity is a math equation that's always true no matter what the value of the variable is. Okay? And so again, these are words that go together on the homework. Give me thumbs. Okay, good. All right. Okay, last issue. Literal equations. So literal equations are equations that involve multiple variables. Okay? This is applied math, right? The place where we would use literal equations is when we're trying to use either math or geometry. We're using formulas, essentially. Like, let's take this formula right here. This is the formula for the circumference of a circle, right? We have the formula C equals 2 pi r, where C is circumference, r is radius, right? So this allows us to predict, if I know the radius of a circle, it allows me to use this formula to predict the circumference, right? If the radius is 10, then I get 2 times pi times 10, whatever result that is, 20 times pi. That's what I should expect the circumference of the circle to be. I can make a prediction, okay? But what if I know the circumference and I want to calculate the radius? That's not a very useful way to write that formula, is it? Right? If I'm trying to predict the value of the radius, if I know circumference, wouldn't I rather have r equals something? Have the r by itself? Because that's the value I'm trying to calculate, right? Everybody give me thumbs on that. Does that concept make sense? Okay, so then what would I do if my goal here is, we're not going to solve for pi. We're going to do something different. What if I want to solve this for r? What would I do to solve that for r? Now, it looks complicated, but it's the same rules as before. Go ahead. That's it, right? I do the same stuff as before. I'm going to follow my order of operations tree. And look, I can point to a single r here, right? So I should be able to isolate it by using inverse operations. Well, there's only one thing to do. I just have to undo multiplying by 2 pi, right? So if I divide each side through by 2 pi, the 2 and the pi cancel, and I get the result, r equals circumference divided by 2 pi. Now, there's a formula I could use. If I know the circumference, all I have to do is to divide that circumference by 2 pi, and it's going to predict the radius. You get the idea? Okay? Same kind of thing like if I were going to do in physics. let's say I was going to use Newton's second law. So I've got force equals mass times acceleration. Okay, so what this tells me is if I know the mass of an object and I can measure its acceleration, Newton's second law predicts what the force acting on the object is, right? So if I've got an object with a mass of 10 kilograms and the acceleration is 10 meters per second squared, those would be the units we'd use. I'm going to get 10 times 10, I'm going to get 100 for my force in the same units called newtons, right? That we're not really, I mean, that's going a little bit more into physics than we probably need to, but it's a good way to illustrate this. So that's a valuable formula for me to use if I know M and A and I want to calculate F. But what if, for example, I want to calculate I want to predict the acceleration of an object if I know how much force is acting on it and I know what its mass is? What am I going to do if I want to predict A instead of F? Good, I want to get the A by itself, don't I? I want to isolate the variable that I'm looking for, is what we do in science. So I'm going to isolate the A, and the only thing I have to do to get the A by itself is just divide by M, right? So the M's cancel, and I end up getting A equals F divided by M. So now I have a new formula. I could predict the acceleration by just dividing the force, which I know, by the mass, which I know. Okay, give me thumbs. Okay, you get the idea. All right, let's just practice a couple of these. So what about this one? I've got some formula up here, and I want to solve this for the variable v. In this case, we don't know what these are, but we'll just assume it means something. Say it again. Okay, so how many people, that's the first thing they do is distribute the 1/2? Give me a show of hands. Okay, a few people, yeah, and that's okay to do. It's okay to do. You're used to doing that. It's fine, but I'm going to show you maybe even a little bit slightly simpler way. If we really follow the rules for order of operations, what did we say about order of operations earlier? Last week. Remember, we said that we're going to simplify until we can isolate a single variable. And as soon as we can isolate a single variable, we're going to use inverse operations to isolate it. Well, there's only a 1v in that equation, right? There's the v. I should be able to isolate this without doing any simplifying. I shouldn't have to multiply that 1/2, distribute that 1/2 through. Okay, but I will point something out. Notice that when we use inverse operations, that we don't get to the parentheses until the last step of inverse operations. Well, I have some parentheses there, don't I? So I don't even get to worry about what's in the parentheses until after I take care of everything outside of the parentheses. So effectively, we could just cover up what's in the parentheses and not even worry about it for now. So let's just do this. I'm just going to cover that stuff up because we don't get to the parentheses until the last step. So now, outside of parentheses, my goal is to isolate the v. I should be pushing stuff to the left, right, to get rid of stuff from the right side so I can isolate the v on the right side. Is there anything outside of parentheses I need to add or subtract? Thumbs up for yes, thumbs down for no. Outside of parentheses, anything I need to add or subtract to both sides? Okay, I'm seeing lots of thumbs down. That's correct, right? Don't have to do any addition or subtraction. Outside of parentheses, is there anything I need to multiply or divide both sides by? Now, right now, look, the parentheses are being multiplied by a 1/2 outside of the parentheses, right? My goal is to get everything away from the right side and push it to the left side. How do I undo multiplying by 1/2? Okay, divide by 1/2, but what do we do with fractions? Do we divide by a fraction? Oh, good, we multiply by the reciprocal instead. It's easier, isn't it? So we'll undo multiplying by 1/2 by multiplying each side through by 2, right? So there's our first step. How come we do that? Because the 1/2 times the 2 cancels. Just get 1, right? Everybody see that? Okay, now, finally, we got rid of everything outside the parentheses. So now, finally, we can move up and focus on the inside of the parentheses. Okay, so now what's left here? We got rid of everything on the outside. So now all that's left is what's inside the parentheses. W plus V equals 2 times 7 is 14W, right? Okay, so finally, now that we're in parentheses, what's the last step I need to get that V by itself? Subtract W. There you go. Okay, so the W's cancel. And look what happens. I get the V by itself. 14W minus W is 13W. There it is. Okay. All right. How about a little more practice? How about that guy? Now, it's always helpful to write in implied parentheses when you're doing these kinds of problems. Are there any implied parentheses that I could add there? They're not written, but they're implied. What stuff is grouped in that problem? Ah, the A plus B, yeah. And that's because of the fraction bar, right? You told me that a couple weeks ago, a bunch of you. So when we have a big fraction bar, everything on the top and the bottom is grouped. The bottom only has one thing, so we don't really need the parentheses. But the top, there really are parentheses there. Even if we don't write them, we know they're there, right? Okay, so we're going to isolate that B. I can point to a single V, so I can isolate it. Now you just need to tell me what steps I'm going to use in what order to isolate that B. So outside of parentheses, thumbs up or thumbs down. Do I need to add or subtract anything outside of parentheses? Good. Lots of thumbs down. I don't need to. Skip. Do I need to multiply or divide by anything? Yes. What? C. Good. I want to undo dividing by C, and I undo division by multiplying, right? So I'm going to multiply each side through by C. There's my first step. So those C's cancel, and then look what I get. My parentheses, A plus B equals 5C. Last step to solve for B. What's the last thing to get that B by itself? Yeah, subtract A, right? So we go subtract A. So those guys cancel. And I get B equals 5C minus A. Okay, give me thumbs. How we doing? Okay, I'm going to give you this is a doozy. This is a tough one. How about this? This is, what the heck is this? This is, I don't know, that's a weird geometry. That's a volume. That'd be a pretty weird shape. I'm not sure what that looks like, but it's pretty bizarre. We're trying to, they give us the volume. V equals 4/3 pi HR squared plus 2/3 pi R cubed, right? We're supposed to solve this for H. Can I point to a single H? I can't? I can. There are multiple R's, but I can point to a single H, right? So I should be able to solve this thing if I just follow my order of operations. Okay, I just got to follow the, I know it looks complicated, but if you write this down and you just follow these steps, it works out. Okay. So what's the first thing I've got to do then to get that H by itself? Is there anything I need to add or subtract to both sides? Now, here's how you want to think about this. Every step I make, I'm trying to get closer and closer to having the R by itself on the right side of the equation, right? So every step I do should be moving stuff away from the right side over to the left side. What's the first? Is there anything I could add or subtract to get rid of stuff from the right side? Yeah, look at that whole term right there, right? I've got this R, this H right here that's included in this term, but then there's this whole other term that's being added to it. I want to undo that one, right? Okay. You can almost think of this, and if this doesn't work for you, just ignore this. But this is kind of a good way to think about this. It's almost like in chemistry, it's easier to strip away parts of a molecule that are held more loosely, right? You want the stuff that's bound the weakest is the stuff that you can pull away first of all, right? And then it gets harder and harder to pull parts away from it depending on how strong the bonds are. Well, the weakest bonds to break here is just adding or subtracting something outside of parentheses, right? Everybody see that? This is not included in parentheses. So here's the first step. I'm going to undo that by, let's go to the next page, by subtracting this from both sides. Okay, look what happens. So over here, those guys cancel, right? I just canceled those by subtraction. What do I end up with on the left side? I've got v minus 2 pi over 3 times r cubed. Those are not like terms, are they? I can't combine those. So I'm stuck on the left side with v minus 2 pi over 3 r cubed. I can't combine them. I'm just going to subtract this from v. On the right side, I've got my 4 pi over 3 h r squared. Okay, now what? So with order of operations, first thing we did was we subtracted. Is there anything I need to multiply or divide both sides by? Trying to get the h by itself. Okay. I could divide each side by 4 pi over 3, but with fractions, instead of dividing, we multiply by the reciprocal, right? Okay, so I could do this. I could multiply both sides through by 3 over 4 pi, which means I need to put that in parentheses, right? Because I'm multiplying the whole side by something. Okay, so I've got 3 over 4 pi. So that cancels that, right? Everybody agree? If I multiplied straight across, this times that, I'd get 12 pi over 12 pi. So they cancel. Okay, give me thumbs. This is a pretty big time problem. So what are we left with? I'm left with 3 over 4 pi times the quantity v minus 2 pi over 3 r cubed equals h r squared. Well, that's what I'm trying to isolate. So what's the only other thing I have to do? Okay, divide by r squared, right? Everybody agree? Okay, now we can do that and it's fine. But dividing by r squared, being as I already have a fraction over here, dividing by r squared, does everybody see that's the same thing as multiplying by 1 over r squared? Prove it to you. Like if I have 12 divided by 4, that's the same thing as 12 times 1/4. They're both equal to 3, aren't they? Everybody agree? So in this case, it might actually be more convenient, rather than dividing by r squared, because I've already got a fraction here, let's multiply by 1 over r squared. And I still get r squared over r squared, so they'll still cancel, don't they? Right? Those guys cancel, and we got it. We got h by itself equals, what do I get over here? Well, if I multiply straight across, I get 3 over r squared times 4 pi. So I'm going to write that as 3 over 4 pi r squared. Usually we put the variable last, not a big deal, times the quantity v minus 2 pi over 3 times r cubed. Okay, my point is we're done, right? The answer can look really ugly like this. It's okay, we got an ugly formula, but that's the answer, right? Everybody see that? Okay, whatever we get when we get the h by itself, that's the answer. Okay, when are we out of here? Okay, we're done. You guys got work day tomorrow.